Today is one of the longer topics of the whole semester. It's the law of sines. It's a method of solving certain triangles that you apply for non-right triangles. We've been solving right triangles using right triangle trigonometry. What if the triangle isn't a right triangle? Turns out you can always do this. Let's just mention this real quick. If I have a triangle that's not a right triangle, and I'm given two pieces of information other than angle, angle, angle. Maybe I'm given an angle, a side, and an angle. I can solve this triangle by dropping a perpendicular here and making two right triangles out of it. It always works, but boy, if you think about it, it's kind of difficult. You're breaking C up into two pieces. You have to write two equations and two unknowns. It's actually a hard problem. So non-right triangles are difficult to solve using right triangle trigonometry, even though they can be done. I see engineers do this sometimes. They don't want to go back and remember the law of sines. When you get a non-right triangle, there's going to be two rules that are a lot easier than breaking it up into two right triangles. It's the law of sines and the law of cosines. Those two theorems. Today we'll do the law of sines. It's a really long topic. I usually break this up into two lectures, but I didn't want to break the video into two pieces, lest I lose the momentum of it. So I'll try and do it all at once, but this is really two lectures. And then we'll do the law of cosines next time. And with the two of them together, you'll be able to solve all non-right triangles easily instead of breaking them up into pieces. The law of sines applies to these kinds of information. The idea is you'll be given three things of a triangle, not angle, angle, angle. That's sort of only two things, because if you know two angles, the three add up to 180, so you automatically know the third, right? It's not a congruence identity, angle, angle, angle. You can have two triangles like this one, and one that's exactly twice as big with the same angles, or 10 times as big with the same angles. Angle, angle, angle isn't a congruence theorem, so you can never solve the triangle given that. But any other three things, you can either solve the triangle, or you can find all the possible cases for the triangle. So that's what we're going to do today, is these three cases: angle, angle, side, angle, and side, angle. If you're given those three things, we can solve the triangle or say all the possibilities. And then next time with the law of cosines, we'll do side, angle, side, and side, side. The only other arrangement of three pieces of information is angle, 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 and that's not a congruence identity. So we'll get everything between the law of sines and cosines that we can do on non-right triangles. In each of these triangles, for convenience, to save us notation, we're going to assume that the sides are labeled A, B, and C. The angle opposite A is alpha, the angle opposite B is beta, and the angle opposite C is gamma. So this will be the basic setup on every single triangle for the law of sines and the law of cosines. And here's the law of sines. I didn't write down the proof of it. I don't think it's worth doing on this thing. But look how easy it is. Sine alpha is to A, as sine beta is to B, as sine gamma is to C. That's the law of sines. That's all you need to memorize for this chapter. The rest of it is all learning the techniques, and they're kind of difficult, actually. And we can do some very fun problems. For instance, you've seen the Leaning Tower of Pisa, right? It's this terrible tilt. I wonder how much it's tilted. I'm going to show you today how you can know the height of the tower from the specifications, pace off the distance and measure the angle of the top, and figure out exactly what the tilt is. We're going to do that today. Lots of neat problems like that. Problems like triangulating to find a lost person in a boat out at sea if they're not too far away, so that the curvature of the earth comes into effect and you can treat the earth as flat. You can use the law of sines to solve find the survivor problem by triangulation. So lots of neat applications in these too, and we'll see some more with the law of cosines. This is all we're going to need for a theorem today. Here's the first case. We said we could solve a triangle given an angle followed by an angle followed by a side. Suppose we have angle beta, angle gamma, and side B. This is, if you look at the triangle with beta, gamma, and B. Let's look at the triangle up above for a second. Beta, gamma, and B. rotating around the triangle, I have an angle followed by a side. So that's angle, angle, side data given. That says we use the law of sines rather than the law of cosines, because it's one of the three cases we mentioned for the law of sines. Suppose I have these three values. Round your answer to the nearest tenth. So that means one place after the decimal point, right? What we do is we can immediately write down the law of sines. Sine of beta is to B, right? As sine of gamma is to C. And the idea here is to always put three numbers you know into one of the law of sines. This is actually three laws that we see here in the law of sines. Let's put it back up. We have this equation, and this equation. So the law of sines has really three equations. We'll use this one here. Sine beta is to B as sine gamma is to C, this last one, right? And three of the numbers known, we can solve for C. We simply, there's lots of algebraic ways to do it. You can do whichever way works better for you. I like taking the reciprocals of both sides. I'll say, if these two are equal, then their reciprocals are equal. 10 is to sine 95, turning this one upside down, as C is to sine 30, turning this one upside down. Now, all I got to do is multiply both sides by sine 30, canceling this one and leaving 10 sine 30 over 95, sine 95 on this side. On my calculator, I run this, and I get C is equal to 5.01909, blah, blah, blah. If we're going to round it to the nearest tenth, this place right here, then we take the next digit after that, and if it's 5 or greater, we round this up to 1. If it's 4 or less, we leave it as 0. Well, it's 4 or less, so we leave this as 5.0. We write the 0 to indicate that is a significant digit. We don't write 5. All right, so now we round this to two places so that we've rounded it to the nearest tenth. Now, once we have two angles, we could have done this on the first step, in fact. We can always find the last angle because the 3 add up to 180. Alpha, the remaining angle, is 180 minus the 2 we're given, is 55.0 degrees, I'll put, because I said round to the nearest tenth, right? All right, now finally, that we have alpha, we can say sine alpha is to A as sine beta is to B. Now I can also use as sine gamma is to C because I know both of those. But one slight piece of advice, when you use rounded numbers, again in the second equation, and round a second time, sometimes there's a tiny bit more error than if you just use the original numbers that were only rounded once, presumably coming in. And every time you round, you lose a little accuracy. So you can use whichever ones you want. You can use sine gamma over C, I'll count it perfectly correct. But since I have beta and B in the original problem, I'll use those in here to get as little rounding error in here as I can. And we'll say these are equal by the law of sines. And now I can solve for this. I'll do the same thing. I'll turn both sides upside down. 10 is to sine 95 degrees, as A is to sine 55 degrees. And you know, some books actually put the law of sines upside down. They'll put A is to sine alpha, as B is to sine beta, as C is to sine gamma. All three of these upside down, just because this comes up so often that you have to turn them upside down. However, there are other cases where this is more convenient, so you can remember the law of sines whichever way you like it, this way or the upside down way. Books use both of them. All right, if you would have memorized it that way, you could start right here and save a step, right? So if you want to do that, just remembering this can be upside down, that's fine. Now once I have this, I multiply both sides by sine 55 degrees, and I have A as 10 sine 55 or sine 95. I'll switch sides here. And on the calculator, I get 8.2 to the nearest tenth. There is the solve the triangle. Solve means find all the remaining angles and sides that aren't given here. There's 3 angles and 3 sides. We're normally given 3 pieces of information. That means we have 3 to find. So we have 1, 2, 3. I found all the remaining sides and angles that there are. Let's try another one. And for this one, I want to put in some hints. We could have done it on this one. When you solve this, you notice there's a lot of calculations. I say apply the sanity check afterwards because so many calculations, it's very common to make an error. You know, I do this all the time when I get down to the end, and you know how it works. The error is usually in the first steps. You do everything over, but that's one of Murphy's laws we talked about. Well, Murphy-like law. I don't think it's in the official list. The longest side of any triangle is always less than the sum of the other two sides. I started to put less than or equal because what happens in practice is with rounding, sometimes they come out to be equal. If you carry enough digits, then the longest side will always be less than the sum of the other sides. Once in a while they come out to be equal because they're rounding. But why would that be? How do you know the longest side is always longer than the sum of the other sides? It's the shortest distance between 2 points is a straight line. If this was bigger than b plus a here, right, then this distance would be farther than going this way followed by this way. The shortest distance between 2 points wouldn't be a straight line. So what you can do is, like in that last example, see if the longest side you found is it has to be less than the sum of the other two sides or your answer is wrong. All right. The second thing is you can check when you're all done with the three angles add up to 180 degrees. That's true of any triangle, so just add them up and it's a double check. It's an easy one. These are all easy. Kind of like when you want to know what the weather is, you don't want to run out to the TV or something, right? So you put your finger up in the air, wet it, see which way the wind is blowing, you know maybe what way it usually blows right before the rain comes or something. You know, so it doesn't give you a real accurate result, but you know, real surety what the weather's going to be, but it's easy, right? So these are easy to check to see if you've made a blunder somewhere along the way. This actually does, however, catch most of them. If you're good with your finger, you can usually tell when the rain's coming, right? Here's the third one, the three bears test. This is true of any triangle too. The longest side is always opposite the largest angle. The medium side is always opposite the medium angle, and the smallest is always opposite the smallest angle. I call it the three bears test, right? Because the three bears were like that, right? Papa bear had the biggest, and Mama the medium, and baby bear the smallest, always, and everything. So you do the same thing with triangles, and often you'll catch a mistake that way. These three tests catch almost every insane mistake you make, right? So then the second hint here is on a calculator with a computer algebra system. If it says CAS on the display, like you have a TI-89 or HP Prime or a Casio ClassPad, there's getting to be others, you can run into a problem actually doing those calculations we just did on the last page. I just wanted to point out. You can take all those numbers and multiply them together, and if you just put in whole numbers without decimal points for the sides, sometimes it'll give you the answer in terms of a sine or a cosine or something like that, and you'll say, why didn't it give me the decimal? They default to this best mode where they sometimes, if they put the exact answer as the sine of an angle, they'll leave it that way. And in order to get a decimal answer, you have to put a decimal point on at least one of the numbers going in. Then it says, aha, that's a rounded number, I'll round everything and put the decimal point in, and then it will give you the decimal answer. So if you're dealing only with whole numbers and you're using a CAS calculator, make sure you put a decimal point on one number. If you forget, like I always do, and you get down the answers in terms of some crazy sines and cosines and all, just multiply it by 1 point, and it assumes this is a rounded number, and it rounds everything and gives you the decimal. You can also put the calculator into approximation mode if you prefer, then it will always give you decimal. There is, if you push the mode key, you can go there. So there's some calculator hints. The final thing is, this is all great. The theorem says for any triangle, this works. It doesn't matter. It's true for any triangle, but if you have the two cases for law of cosines, side, 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 or side, angle, side, it's real hard to work with, just like the case I showed you for right triangles. So don't do that because it's clumsy. You wind up with multiple equations and so forth. And also for right triangles, don't use this because right triangle trigonometry is faster. Just to remind you. Let's see. Oh, it went off again. Here's the famous photo by Newton 2 from Wikipedia. And here's a woman looking up at the tall tower, and she says, I wonder how tall that is. Don't use the law of sines, right? You've got a right triangle here because the ground is horizontal and the building is vertical. Just say that the tangent of 50 degrees is this over this, and so h is 40, tangent 50. That's a lot easier than using the law of sines, right? So we'll make that mention. Use the law of sines for non-right triangles with one of those three cases that we mentioned. Angle, angle, side, angle, or side, side, angle. Here's the next example. We did the angle, angle, side problem. How about an angle, side, angle problem? Suppose I'm given alpha equals 37 degrees, beta equals 49, and c equals 5.0. If you look on that triangle, you'll see rotating around is an angle followed by a side followed by an angle. You can tell it if it's alpha, beta, and the side that goes with gamma, c, then this is the one between these two. So the one that goes with the other letter is between, if you want to memorize it that way. All right, here it is. Gamma is up here. So if you have, alpha, beta, and the side that goes with gamma, then you've got angle, side, angle, right? All right, so now what we can do, since we know two angles, and a nice thing to do, I think, always, I didn't do it in the last problem, but is to just take 180 minus the 2 you're given, you have the last one, right? So this last angle is 94 degrees, and now we can use the angle, side, angle to solve this one. So we have sine 94 is to 5.0, that's sine of gamma is to c, as sine of beta, 49 degrees, is to b. Three numbers that we know now, and one we don't. On the angle, side, angle, by the way, you always have to find that last angle first, because otherwise you won't be able to get three of the four things known. And that's what you want, is three knowns and one unknown to solve for. Well, this time, just to be different, I'll show another algebraic way people often like to solve these things. Cross multiply. When you have two quotients equal, then this times this equals this times this, right? So you have b times sine 94 equals 5.0 times sine 49. There's cross multiplying to solve this one. Now I can divide by sine 94 degrees and I get this. b is sine 5.0 sine 49 over sine 94. On this one, instead of saying round to the nearest such and such place, I'm going to say use correct rounding. Number of significant digits are the least in the calculation whenever you use multiplies and divides and the trig functions. This doesn't apply to subtractions, but here in this subtractions you use significant digits, you round where the first number runs out of digits. So they all run out of this one is exact. These two run out of digits at the decimal place, so we round this at the decimal place. That's what happens in subtractions. In multiplications and divisions, you round to the number of digits, significant digits, that's the least number of those numbers going in. These numbers all have two significant digits. This 0 means that's a significant place. So I'm going to round my result to the least of those to two significant digits also. So in this one, for correct rounding, these have two significant digits, I'll round it to significant digits. So when I calculate by algebra, b is this over sine 94. The calculator tells me 3.7827 blah, blah, blah. This time, if I want to round two places, 1, 2. For significant, you start with the leftmost non-zero digit and you count. 1, 2. This is the last place I'm going to keep. If the next digit is 5 or greater, and it is, then I'm going to round up this time to 3.8. So there's the answer there. And the idea is that if you carry any more digits than garbage, depending on how these were rounded coming in, the next digit could be anything. So there's no point in carrying it, just round it there. Now finally, we have b, we can, and gamma, we have three things, we need to find two things. 1, 2, we need to find a still, is the one thing we don't have, so we write sine alpha is to a as sine 94 degrees, gamma is to 5.0 c. Again, I'll use these two numbers. And now if I cross multiply again, I have a times sine 94 equals 5.0 times sine 37. I'll divide by sine 94 and switch sides, and I've got a is 5.0 sine 37 over sine 94. rounds to 3.0, carry that 0 since it's significant. There's the 3 things to complete that triangle. We might apply the 3 things, right? Do these angles add up to 180 degrees? Let's see. 37 plus 94 plus 49. Sure enough, 180. All right, and then I take the longest side. Let's see, was 5. That's shorter than 3.0 plus 3.8. So that's that test. And then I want to make the largest angle opposite the largest side. The largest side is C, the largest angle is gamma. Second largest side is 3.8, B, so the second largest angle must be beta, and sure enough it is. And then alpha and A will be both the smallest automatically. So there's the sanity check to make sure that was all right. And I just thought for fun I would point out that this angle side angle case is the one that's often used in triangulation to find a lost survivor, right? Help out here. So you can figure out the angle where their signal is coming from each of these stations. You know the distance between the stations and the angle between them, so you can figure these 2 angles and the distance between. Now look, you have angle, side, angle. You can solve the triangle and figure out exactly where the survivor is if the curvature of the Earth isn't too great. If the curvature of the Earth is too great, there's something called spherical trigonometry that isn't hard to figure out once you've picked up plane trigonometry. It just takes a little while, but it's not hard once you know this. So you can actually find them further away with triangulation also. You just have to use spherical trigonometry. All right, here's the next problem, the fun one for the day, right? The Leaning Tower of Pisa. Look at, I'd be afraid to slide off there, right? This building has been fixed over the years. It started to tilt so far they got worried about its structural stability and they tried to upright it a little bit. They didn't put it all the way straight. Nobody would come to see it anymore, right? So it's got a certain tilt that they feel okay with. But it has changed a little over the years as the ground settles. That was the original problem. They built it on shifting sand, and you know what happens then, right? The thing doesn't stay up straight when the ground gets wet. All right, so beautiful building, right? How far does it tilt, we wonder? Well, if we know from the specs that it's supposed to be 56 meters tall, and we walk 25 meters from the middle of the building and measure up to the top and at 73 degrees, we can actually say, let's see, side-side angle rotating around. We have side-side angle data, the third case. We can solve this triangle. All right, so let's see how that goes. Oops. Find the tilt of the Leaning Tower of Pisa if it is all those things that we just said, right? For an applied problem, I highly recommend you draw a picture. That is of immense help. It often just keeps you from, again, blundering or making a stupid mistake, right? So, and it's going to help us here. Alpha is the angle up, if this is the tower sitting right here, is the idea, 56 meters tall, just like in the picture. And we went off 25 meters and measured 73 degrees. Then what do we know? We know angle, let's see, side angle rotating around that way, we said. And so we can apply the law of sines, right? We'll say that this, let's show the next step here. The sine of 73 degrees is the 56 meters, its opposite side, as the sine of beta is its opposite side, 25. That's the law of sines. Right? So now we need to find beta. So we multiply through by 25 and get beta. Sine beta is 25 sine 73 over 56. So sine beta is 0.42692, etc., etc. What's beta? We remember our inverse trig, right? Beta must be the inverse sine of 0.42692, etc., etc. Here's what you do on your TI-84 or TI-83. They're virtually equivalent. You take second sine to invoke the arc sine. Then you push second minus, which has ands above it, to put in the last answer, and it will carry all the decimal places. How many times I've fat fingered this thing trying to punch in a number and get it wrong. Instead of fat fingering this, put second sign, second answer, and it will automatically get all the digits correct. On a lot of calculators, you may need to close the parentheses, the older ones. The new ones usually have to, and you may not need this step on those. But arc sine of this number comes out to be about 25 degrees in the nearest degree. This time we'll round to 2 digits, since these were all carried in 2 digits. Just like the last problem. Now we have 2 angles. We can take alpha as 180 minus the 2 we know must be 82 degrees. Once we know alpha, it follows that the angle we want of the tilt is 90 degrees minus alpha, right, since these are complementary angles. So it's tilted 8 degrees according to this calculation. That's reasonably close. Look on Wikipedia to see what the exact tilt is these days, but this is a good approximation. All right, well, let's try this on the calculator now. I have to calculate 25 sine 73 over 56. I'll put 25 point, as though I was doing this on one of those computer algebra system calculators, just to make sure it gives me a decimal. You don't have to do that on this calculator. TI-84 doesn't do exact answers. Times sine 73. Here's a common mistake, is to forget to close your parentheses on one of these old calculators. If you have a calculator that doesn't automatically put in 2, put in the parentheses here before you divide by 56. Otherwise, it will automatically close all your parentheses after the 56 and take the sine of 73 over 56 instead of taking the sine of 73 and then dividing by 56. So, common calculator, important thing, make sure you close all the parentheses on your trig functions. Now I push the enter. Uh-oh. What in the world could I have done there? Here's the second common problem. Your calculator is in radians mode. There it is. Go down and put it in degrees mode. Double check. Sure enough, now it's in degrees mode. So let's try it again. 25 point times sine 73 divided by 56. There we go, a more reasonable number, right? So those are the 2 common calculator errors. And sure enough, we get this. Now if we want to take that and avoid making an error by not typing in the number correctly, we can push inverse sine. We push second sine. The inverse sine is above the sine, just like so many other functions are. The square root is above the square, right? The exponential is above the logarithm, and so forth. Arc sine, and we'll push second, followed by the little minus key down here, and we'll put the answer in there. Now I'll close my parenthesis. What's the arc sine? There it is, 25.27, etc. degrees, which rounded to 25 was our answer. So there's an example of using the calculator to calculate these things, and some calculator mistakes that are easy to make. Well, if that's one mistake, there's an even more horrifying mistake that can go on in the method itself. These problems, more than almost every other section, require lots and lots of practice. There's a lot of different cases, and unless you practice all the cases, you'll find you'll fumble on the test, not knowing what to do because you're trying to do the wrong case. Side-side angle is actually an ambiguous case in general. There's often more than one answer. You can actually get 0 answers, 1 answer, or 2 answers, because maybe you remember from geometry, side-side angle isn't a congruence theorem. Those other 4 we mentioned are angle, angle, side, angle, side, angle, side, angle, side, and side, side, side are all congruence theorems, but angle, angle, angle is not, and side, side, angle is not. Angle, 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 you don't know anything except, triangles are similar, the same angles. But in side, side, angle, here's what can happen. When you get down to that step in the last example with the leaning tower of Pisa, I took beta equal arc sine of x. That was a possible mistake. If I know what the sine of an angle is, beta isn't necessarily the arc sine. It could be one angle whose sine is x is always the arc sine, right? Assuming x is between -1 and 1, so it has an arc sine. But there's always another case. If you solve for all angles such that sine beta equals x, y, I guess I should have put, then you put sine beta equals y, this coordinate here, I should put y. Look, there's two different angles. This one and this one both have that sine. This one is the arc sine. I wonder what this one is. Well, if you think about it, by symmetry, if this is arc sine, this also has to be arc sine. So this angle here is 180 back up arc sine. It's always 180 minus arc sine. So whenever you have sine of beta equals a number, arc sine is one number between minus 1 and 1. Arc sine is one number. I should fix this, maybe just to make it more reasonable. There we go. Y. So arc sine of a number between minus 1 and 1 is always an answer, but 180 minus the arc sine is always an answer too. And unless this is 90 degrees, there's going to be two answers. All right. Now, let's apply that to this problem. Suppose I'm given this triangle and I dutifully draw it out because I saw how much it helped me in the Leaning Tower of Pisa. Oh, by the way, we have the right answer in the Leaning Tower of Pisa because the tower was leaning this direction. We knew the angle of its tilt that we were finding was acute. The acute angle is the arc sine, right? The arc sine is always a number between plus and minus 90 degrees. We can't get negative angles in a triangle. So what will happen is we'll get an angle between 0 and 90 is the arc sine. Since the leaning tower is leaning this way, making an acute angle, we knew it was arc sine, not 180 minus the arc sine. So see how useful drawing the picture is? So now we'll try drawing a picture again. We'll say, suppose I'm given this side is 24, this is 21, and this angle here is this angle here is 55 degrees. And I want to find alpha, like I did in the previous problem, and I want to find beta, and I want to find b. I want to find the three sides that aren't marked on there, the three pieces of information that aren't marked on there, so there's b also. Well, we can say by the law of sines, we'll use the three things we know, right? 24, 21, and 55. And we use this angle on its opposite side. The sine of 55 is to 21, as this is to the sine of this angle is to 24. Right? So we get this from the law of sines. Sine of an angle to its opposite side is sine of another angle to its opposite side. I put next there, that should be alpha, shouldn't it? Could I change it? Sine alpha. And now, that means that sine alpha, just by algebra, how about multiplying by 21? I'm sorry, sine alpha is 24 sine 55 over 21, multiplying by 24. All right, and if sine alpha is equal to this, alpha could be the arc sine of 24 sine 55 over 21. Here I won't even calculate the intermediate result. I'll just I'll say alpha is the arc sine of this number, and I'll calculate it all in one fell swoop on the calculator. I come up with 69 degrees, taking arc sine of 24 sine 55 over 21. Carefully closing my parentheses as I go. But the other angle it could be is 180 minus the arc sine. I wonder which one it is. In that case, I get 111. Well, the answer is it's both. Both triangles work. Despite that we drew this out, it turns out there's two different solutions that both work. So in case one, we have 69 degrees for the arc sine. If I take that together with the given information of 55 degrees here for gamma, then beta is 180 minus 69 minus 55 is 56 degrees. I have the last angle. Now I've got only one thing more to do. Right? I found two, I need one more. So I apply the law of sines. The sine of beta is to b as sine of, what was 55 degrees, I've forgotten, gamma is to c. Alright, so this one I can solve for beta. I take the reciprocals of each side, multiply by sine 56, and I get b is 21 sine 56 over sine 55. That comes out to be 21, and that's one possible triangle is to fill out these three, but there's one more case. If I use alpha equals 111 degrees, beta equals 180 minus 55 minus 111 is 14, tells you that there's another case. Sometimes there's not. If you get a negative number, that means there's just not a second case. We'll talk about that shortly. But since this is a non-negative number, there's actually, since it's a positive number, there's actually another triangle that has this angle, and this one, 180 minus these, and we just need to find the last side. So we again apply the law of sine. Sine of 14 is to b, sine beta is to b, and sine 55 degrees is to 21. And solve for b by reciprocals and multiplying by sine 14 gives that b is 21 sine 14 degrees over sine 55 degrees, comes out to be 6.3. How can that happen that there could be two answers? Well, you've got a nice picture in the book. Every trick book does it. You can look it up online if you want to verify it. But here's the case. Suppose I'm given side-side angle data like that. A, B, alpha, for instance. Well, if A is longer than B, if you think about it, this angle is fixed, but this angle can be anything, right? I just know the side lengths and I know this angle. So I can rotate this side around anywhere I want. Where can I intersect an angle, a ray going in this direction to complete a triangle? Only where I tilt it right here. Over here, it won't make a triangle, right? The only way I can intersect a ray coming out from B this way is to turn it right here. And so there's only one triangle, one solution when A is greater than or equal to B, it turns out. Always one solution. But there's another case. You might have A, this side is opposite the angle given, less than B. Now you've got three different cases. It might be this case where there's two triangles. This is the last one we had. We had A and B and alpha, or another side-side angle case. One of the angles is, in one case, you get an arc sine opposite B, and it's acute, and the other side you get an arc sine and it's obtuse, right? Less than 90 degrees here and bigger than 90 degrees here. This is the triangle with the arc sine in it, and this is the triangle with the 180 minus the arc sine in it. And you get two different cases. And the idea is that, again, A can swing around and a circle of rays here, and this time it can intersect the ray coming out either right here or right here, and so it can form this triangle, or it can form this triangle by intersecting along the circle at one of those 2 points, and satisfy all the conditions. Another possibility is that the angle here is such that when I swing side A around, I can just touch it at one point at a right angle, then I have exactly one solution again. Or it might be that A is less than B, and this angle is too big, and no matter where I swing A, I can't intersect this last side, and then there's no solution. So if A is bigger than or equal to B, there's one solution. If A is less than B, where you're given A, B, and alpha, then there could be two solutions, one solution, or no solution, and you just have to try it. A nice idea is to draw it. A lot of times you can draw it and pretty well tell, unless it's real close, a real close case. A lot of times you can tell by looking at it. But again, if you can't tell by looking at it, you can always just go to calculate it. When that second angle comes out to be negative, you know there's no solution. So here, let's try another example here. Told you this is a long topic, 2 lectures, even though I'm going double speed here. I'm having to really work at a side-side angle with one solution. Here, we did the case with 2 solutions. You just put beta equals arc sine and beta equals 180 minus arc sine, solve for the 2 triangles. This one will turn out there's one solution. Suppose I'm given A is 220 meters, B is 100 meters, and alpha is 50.0 degrees. These are given 3 significant digits, right? Start from the leftmost digit, 1, 2, 3. There is some ambiguity here. Sometimes if it's before the decimal point, you don't know if this has been rounded to the nearest tens or the nearest ones. they have to tell you. Suppose it's rounded to the nearest one. It's the same thing here. So these are three significant digits, and this is 50.0, obviously a significant digit here, you wouldn't write the 0. Solve the triangle, find beta, gamma, and c, right? The other three things. Well, I write down the three things I know. Sine 50 alpha is to its opposite side A, as sine beta is to its opposite side B, 100. Now I put in three of the four numbers. I can solve for sine beta like by 4 by multiplying by 100, and then I switch sides. Sine beta is 100 sine 50 over 220. Beta is then either the arc sine of that number, which is 20.4 degrees, or maybe it's 180 minus the arc sine. Well, you know what, we don't even have to do the calculation. If we do, it'll come out to be negative. But the fact is, we already know ahead of time, B is not the longest side, right? A is longer. Since B is of the longest side, and a triangle can have at most one obtuse angle, one angle bigger than 90 degrees, that has to go opposite A, the longest side. B can't be an obtuse angle. Obtuse angle only goes up opposite the longest side of the triangle. So B has an acute angle on the opposite side. It must be the arc sine, not 180 minus the arc sine. So immediately, when A is bigger than B, we know that beta is the arc sine. We don't have to calculate the other case. These are tedious, aren't they? So we calculated that it's 20.4 degrees. Now, we have, to finish the triangle, that's step 1. Steps 2 and 3, we calculate gamma by subtracting the two angles. We know we get 109.6, but we're only carrying three significant digits, so we round it to 110, right? And now comes up this terrible thing that happens. If we correctly round to three significant digits, beta came out to be 20.4 degrees, this came out to be 110. The three angles don't add up to 180. Maybe in these cases it's worth just rounding B off to 20 and saying, now it looks better, right? So, and this is correct to the two significant digits I list. So now they'll add up, if I make beta 20 and gamma 110 and alpha 50, now they add up to 180 and it looks better for your boss, right? All right, now sine 110 is to c, as sine 50 is to 220 by the law of sines. So I can solve for c by taking reciprocals and multiplying, or by cross multiplying. I get c is 220 sine 110 over 50, comes out to be 270. And one important factor here, in this case I gave you the measures in meters. If measures are in meters of the original of the other sides, then this side must be measured in meters also. So all three sides have to have the same number, same units. If the other two are feet, this one's in feet. Right? Finally, coming to the end. Side-side angle can have no solution. Here, if you draw it, that's a big hint. Suppose A is 3, B is 5, and alpha is 80 degrees. So here's B5, here's A3, and it can swing around in this direction like this. And I draw them about the scale, and I draw this about 80 degrees, almost a right angle. I say, this is not going to be able to reach it, I'm pretty sure. On the solution, on the test sheets, right, no solution. But just to verify with numbers in case I boo-booed my drawing here, right, which I've been known to do. Let's check it. Sine of 80 alpha is to A3, and sine of beta is to B5. So I put in the three numbers I know, and I try and solve for beta. I multiply by 5, sine beta must be 5 sine 80 over 3 is 1.64 something I know immediately now. There's no solution. Oh. Sine of an angle, remember, is always a number between -1 and 1. If I were to get a sine equal to a number bigger than 1 or less than -1, there is no solution. If you put this on your calculator, it'll say domain error. That means you can't take the inverse sine of 1.64. It's not in the domain of arc sine. Arc sine is defined for numbers between -1 and 1 only. So there's how you can tell if you don't believe your drawing or just want to not do the drawing. You can try this, and when it comes out with the domain error, you know there's no solution. Well, I hope that helps. These are hard problems. Do lots of practice with these and send me questions.